This video is about reactions of alkanes. We are going to be looking at the first functional group here, alkanes. This functional group is not very reactive because it does not have any specific functional group, but it does undergo combustion like all organic compounds, and combustion here is just burning in the presence of oxygen. Okay, so for this one you just have to know the reactions for combustion. Okay, when you have excess oxygen in the air, you always form carbon dioxide and water from organic compounds. But if you have organic compounds that contain other elements except for carbon, hydrogen, and oxygen, then you will form other products. For instance, if you have a halogenoalkane, like in the case of chloropentane, we have chlorine, and therefore in the product we will have HCl. Okay, just remember that if your if your organic compound contains something else besides CHO, then you'll form a different product as well. If it's a halogenoalkane, you're going to form HX, and X will be the halogen, in this case chlorine. You don't have enough oxygen in the air and you're burning something, you do not form carbon dioxide, rather you form carbon monoxide. So carbon monoxide is formed when we have an incomplete combustion, okay, because we don't have enough oxygen. We don't have the O2 here, we only have the O1, or monoxide. Okay, if we really do not have enough oxygen, then we don't even form carbon monoxide, we form carbon. So extreme cases, we form carbon instead of carbon dioxide or carbon monoxide. I will let you guys do Google search to figure out the answer to this one later on when you do the self-paced study. I wanted to go through this mechanism. Okay, so what is a mechanism? Mechanism tells us step by step how something happens. And what are we looking at here? We are looking at a substitution reaction where we start with an alkane with hydrogens all around and a halogen, for instance chlorine, and we end up with a substitution reaction. What is happening here is that one of the Cl's from chlorine substitutes with one of the H's from butane, and we form chlorobutane and HCl. It's like a double displacement. Okay, it's a swap. How does this reaction occur? So we are looking for the mechanism for this reaction. How does this reaction occur? Okay, so it occurs using a mechanism called free radical substitution mechanism, and it happens in 3 steps. The first step is called initiation. Okay, beginning, initiation. The second step is propagation, and the last step is termination. Okay, it's very important to remember this. First step is initiation, then propagation, then termination. What do these mean exactly? So here we're going to be dealing with mechanism, and when we do mechanisms, we have to show the movement of electrons. Okay, so the first thing that happens is we have the chlorine compound, and in the presence of UV light, chlorine gets enough energy to break down into 2 equal chlorine species. And what happens here is in the bond between the chlorine, we have 2 electrons. One of the electrons goes to one of the chlorines and the other one goes to the other, so that we form 2 chlorine radicals. So this is called a radical. Okay, a radical is something that has an unpaired electron. If you remember from before, when we were learning about electron configuration, we say we have Ne, and then we have 3s2, 3p5 for chlorine. If we convert this to the box notation, we'll have 2 in 3s, and then in 3p we're going to have 1, 2, 3, 4, 5. So we have an electron here that is unpaired. If you have an unpaired electron, that is called a radical. In fact, if you think about it, chlorine exists as a diatomic because if it wasn't a diatomic, if it was monoatomic, it would be a radical with an unpaired electron, and that would make it very unstable. So to make it more stable, because nature hates things that are unstable. To make it more stable, it combines with another chlorine so that they are more stable. Okay, but in the presence of UV light, this process is reversed, and we get the very unstable and dangerous species called a radical. In this case, a chlorine radical. This kind of breaking down, we're breaking down a bond here. Because we're taking electrons and separating them, we call this homolytic fission. We are taking one electron from the bond and putting it on one side, and the other one putting it on the other side. It's like divorce, because in this case, remember, we form a bond by putting two species together and they share an electron each. And then it's like, okay, now this relationship is over. We're getting divorced. You get what you brought into the relationship, and I get what I brought into the relationship. So it's like a divorce where people get what they brought in to the relationship. So the electron goes back to the chlorine, and the other electron goes back to the other chlorine, and we form two radicals, two chlorine radicals. These guys are very, 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 very reactive. They will react with just about anything, and that is why we have this reaction with alkanes, because alkanes, remember I said they are not reactive since they have no functional group, but radicals can react with anything, and alkanes are part of something, so radicals will react with alkanes. When we're looking at homolytic fission here, we say one electron goes one way, the other electron goes another way. But in most cases, the reactions we see in organic chemistry are heterolytic fission, in which case the two electrons in the bond, they go together to one side, so that we end up with hydrogen that has lost its electron to chlorine, and chlorine that has gained an electron from hydrogen. This is called heterolytic fission. We get two different species after the fission has occurred. Okay, but in the case that we're looking at today, this is homolytic fission, and we get the same species on both sides. And if you notice this arrow, these two arrows here, versus this arrow here, this arrow has one side of the head, and this one has two sides. And this one is one side because only one electron. It shows movement of one electron. And same here, one side. But here is movement of these two electrons. That's why the arrow is like that. So we have two different arrows. One is one head. The other one is double. Moving an electron, one electron. Here moving pair of electrons. The arrows always point where the electron is going to. Point to destination of electrons, and the butt of the arrow shows where the electron is coming from. Okay, so the arrows always point to where the electrons are going, and the butt is always where the electrons are coming from. So going back into our mechanism here, we just covered initiation, which is when you start with a molecule Cl2 that is a non-radical, and you end up with two radicals. Okay, so you use UV light for this to happen. So you're starting with a non-radical and you end up with a radical. And the word initiation should make sense because we are initiating this process. We are starting it. So we're starting to form radicals from no radical. Moving on to the second step of this reaction. Now this is another step where we form new radicals. We are propagating the radicals. So we formed the halogen radicals, yes, from the first step, but now we're going to make more radicals. And the way we make these radicals is by using the existing radicals. So in the propagation step, we have our Cl radical and we react it with our alkane. Like I said, alkanes are not very reactive, but since radicals are so reactive, they will react with just about anything. And in this step, we're going to form a new radical from an existing radical. So here we're going to form a radical on the butane. Don't worry too much about where you form the radical. Like, how do you know that the radical is formed in that position? Don't worry about that. And I'll come back to what you need to do. But for now, you just form a radical on the butane. And then the hydrogen that used to be here now mixes with the Cl radical to form HCl. It's like this radical comes in to steal. Sorry, I'm gonna put hydrogen here. This radical comes in to steal the hydrogen and its electron from butane. And hydrogen and chlorine together, they share their one electron each, and they form a nice HCl that is stable, leaving butane without a hydrogen and its electron, making that remaining part the new organic radical. Over here, we formed it from an existing radical. Okay, so the propagation step, there are many possible products. I just chose to put it on the first carbon because I'm trying to get to my product. And my product, if you remember from the beginning, was 1-chlorobutane. 1-chlorobutane. Because the final chloro is going to be on position 1, that's why I put my radical on position 1. But if my product had been on number 2, on the second carbon, then I would have done the radical here. So basically, when you're doing a mechanism, you're trying to show, oh, this is a possible way that this reaction happened. And you choose because of your destination, you choose how to get to your destination. Okay? It's just a possibility. It's one of the many possibilities that could be happening. And since you are tasked with finding the possibility, this particular possibility of forming a product like this, then you choose your pathway. That will make sense for that. Okay, so again, if my product had been 2-chlorobutane, I would have done the radical on this position, not on that position. The only reason I put my radical in that position is because I'm trying to form 1-chlorobutane. Okay, moving on. We have formed our new radical. And understand that once this radical is formed, it can also propagate and form more radicals. It can go around in circles even. So more radicals can be formed from this. But since we know where we're going to chlorobutane. The next step that we're going to look at will have to be termination. And in termination, we are terminating this crazy radical process. And the only way we can terminate this process is by making sure that there are no radicals. Because as long as radicals exist, this process is going to be going crazy. Radicals will keep propagating. So to terminate, we take 2 radicals, put them together, and they form a non-radical. So for instance, in our case, because we're trying to form chlorobutane, right? And in the first step, we formed 2 of the Cl radicals. And so far, we've only used the one. And the other radical that we formed in the second step was the other radical was butyl radical. So if we put these 2 radicals together, we end up with chloro, and then this one is the original, and this one is from Cl, chlorobutane. So this is the product that we are looking for. But it is also possible that 2 Cl radicals will come back together, right? And they will form Cl2. And it is also possible that 2 butyl radicals will come together and they will form a longer chain. A longer chain with 8 carbons, which will be octane. Okay, so again, to go through this process, the 3 steps in free radical substitution, we have first initiation, in which UV light is able to break a chlorine or halogen bond into 2. It's called homolytic fission because we break the bond. One electron goes to one side and the other electron goes to another side. Okay, we form a radical or radicals from non-radicals. And then we go to the second step where we propagate. And in propagation, we form a new radical from existing radicals. And then the last step, we form a non-radical from 2 existing radicals, and that is termination. Okay, when you're doing problems on FRS in the test, make sure that you label the steps. You have to label the steps. Initiation is first. Sometimes initiation is called homolytic fission, so you should know both terms, because homolytic fission, because you may be asked, the test may use this phrase. The next step is propagation. and the last step is termination. And under each of these titles, you can then show the mechanism of the reaction. Good luck.